All right, we'll go ahead and get started. So the plan for the week is going to be a little bit different. We're going to do a titration lab today, but obviously we can't do that because we're in remote today and tomorrow. All right, so let me show you a couple things. So in Chem 1 course, it's a little bit slow, and I hope that Zoom is smooth. If it's not or my sound cuts off, like put it in the chat because it's been a little bit choppy. I'll mark somebody else here. All right, so anyway, in the Unit 9 folder, which is the current unit. And the thing for the current week, you'll see in the plan for the week, things are a little bit different. So schedule for the week, 510 to 514. Um, so there's this video about titration that you should watch. I put a link for it for the end of yesterday. So anyway, in the Unit 9 folder for the unit for the week, you should watch this video. I won't play it through the Zoom because it won't look so great, but it's a quick YouTube video about the overall plan about titration. The titration worksheet, which if you were in class yesterday, you should have picked a copy of it up. And I was going to give you time today to work on it in the beginning of class based upon the examples I did yesterday. So there's a link to it right here. And if you click titration worksheet, it takes you to the worksheet, or you can find it directly in the folder for this week. And at the top, it has some conceptual, like little fill in the blank questions about the process of titration. And then there are a few problems. So the main thing to do in each of the problems is that you know a concentration and a volume for one of the chemicals. And with a concentration and a volume, you can figure out a number of moles of that chemical. And then with the number of moles of that chemical, you relate that number of moles to the volume of the other one, and that tells you what the molarity of the other solution is. So for instance, here's a soap solution, which is probably basic, has a volume of 25 milliliters, was titrated to the endpoint with 0.5 molar HCl. And then at 15 milliliters of the acid is used, what's the molarity of the soap solution? So you have 0.5 molar hydrochloric acid. That's the concentration of the acid, and you used 15 milliliters of that acid. So if you multiply the molarity of the acid by the volume, that'll get you the number of moles of acid that's used. And then if you divide the number of moles of acid by the volume of the soap solution, then that'll tell you what the concentration of the soap solution is. In all of these are all monoprotic acids. So I'll write the formula in just a little bit and leave it on the screen, but the basic idea is that the molarity times the volume for one substance, which is the number of moles of that substance, is equal to the molarity times the volume for the other substance. So I'm going to give you a little bit of time to work on these problems based upon the few examples from yesterday. And in 20 minutes at 8:55, I'll go over them with you. And if you just don't know where to start or have trouble with it, I can answer your questions in the chat, or like you can wait till we go over them. So that's kind of like what I was planning to do today anyway. The other things you'll see in the course, I had a date for one of the quick checks was incorrect. Anyway, so the pH and POH quick check, which was actually from last week, and it said that it was due Monday. The date that I had it shut off was actually last Friday, so I apologize for that. So if you didn't get a chance to do that, you can do that. And then there's this honors chemistry titration quick check, which is kind of based upon the problems that I'll go over at 8:55, and that's for today. So anyway, in the acid-base escape room, that said it was for Wednesday, but that was based upon the idea of doing the lab today and the escape room on Wednesday. So that's going to be a little different. We're going to do the lab on Thursday, and then the escape room will be for Friday. So you want to hold off on doing that, but it's still in the upcoming list. So anyway, what you want to do now is, yes, you can click like in materials, in the current week. You can either get to it in the schedule for the week, or it's this honors chemistry titration worksheet. And it looks like this at the top. So if you picked up a copy yesterday, and if you have it with you and you took it home, then it's easiest to just do it right on the paper. And then and we'll go over them. And if you already did it, that's cool. Just hang out till 8:55. So let me put up on the screen, I'll do this. So this is what the top of it looks like. And just write like, let's see, at 9, yeah, or 8:55. And the basic idea with titration is that the molarity of the acid times the volume of the acid is always equal to the molarity of the base times the volume of the base. And each side of this equation, molarity times volume, is actually equal to a number of moles. Same thing here. The molarity times the volume is equal to a number of moles. So another way you can do it is take the molarity times the volume of either the acid or the base, whichever one you know both about, and that's a number of moles. The number of moles must be the same as the molarity times the volume of the opposite, the base or the acid. You can titrate with acid or you can titrate with base. Oftentimes we titrate with the base, but you can also titrate with the acid. And to titrate means to put that chemical in the burette and let it run down through. All right, so that's all I'm going to say for right now, but I'll stay in the room. I'm just going to stop. Let's see, I'm just going to stop the recording for a second. Okay, we'll go over the problems in the titration activity. So the very top of it just kind of is a conceptual idea about what titration, the titration procedure is. So the plan is that titration is a lab method where you take some kind of acid or base and you neutralize the acid or base in a neutralization reaction. So titration is a lab method used to determine the concentration of an acid or base in a solution by performing neutralization with a standard solution. At the end point of the titration, that's whenever the concentration of acid and concentration of the base end up giving you the same number of moles of acid and base so that you completely neutralize the acid with the base or the base with the acid. Once it's neutralized, the moles of acid and moles of base are equal. So the plan is that in a neutralization reaction, you have an acid and you have a base and you react them together. If the molar quantity of acid and base are exactly equal, then you end up with water and a salt in solution, and there's no extra hydrogen or hydroxide ions. If you have excess acid, then there's excess hydrogen as a product. If there's excess base as a reactant, then you have excess hydroxide as a product. And what you're trying to do is get to the place where it's completely neutral. So in a neutralization reaction, the number of moles of acid and moles of base are exactly the same. All right, so we got some kind of soap solution. You got the volume is 25 milliliters, and we titrate it to the endpoint with half molar hydrochloric acid, 15 milliliters of acid is used. There's two different ways that you can approach the problem. One is if you want to calculate the molarity, which is equal to, or sorry, if you want to calculate the number of moles, that's equal to the molarity times the volume. Now the molarity, if it's 0.50 molar, then the volume has to be in liters, 0.015 liters, and that comes out to be 0.0075 mole. It's half of 0.015 is 0.0075 moles. And then that number of moles is the number of moles that goes with this volume. So then the molarity of the soap solution is equal to the number of moles divided by the volume. If you take the 0.0075 mole and divide it by 0.025 liters, you get 0.30 molar. Now, another way to do the problem is to use that equation. Let me just check something here. Yeah, another way to do that is to use the equation that the molarity times the volume for like the acid is equal to the molarity times the volume for the base. In this example, I had to change the volume in milliliters into liters in order to get the correct unit for the number of moles as mole. But in this case, I had to take the number of milliliters divided by 1,000 to get the number of liters. And I also had to take the number of milliliters and divide it by 1,000 to get the number of liters. So dividing by 1,000 twice effectively makes it so that the order of magnitude or the size of the number of moles or the size of the molarity is proportional to the size of the molarity for the known solution. In other words, what I'm saying is it's not necessarily important to convert the volumes into liters so long as the volumes are the same unit. For example, I can also get the number of, or the molarity of the base by taking the molarity of the acid times the volume of the acid divided by the volume of the base. So in one step, I could also take the molarity of the acid, 0.50 molar, times the volume of the acid used, that's 15 milliliters. It's okay to leave it in milliliters now because you'll see that unit milliliter will cancel, divided by 25 milliliter, 25.0 milliliter of the base. So 0.5 times 15 divided by 25 is 0.30 molar. The units milliliter cancel out. See, when you convert milliliters into liters, both in the numerator and the denominator, it changes the order of magnitude of the volume from on the order of tens of milliliters to hundreds of milliliters. So taking the volume in liters and this volume in liters gives you the same ratio as if the volume's just in milliliters. So it's actually really not uncommon to just leave the volumes in milliliters and use the formula molarity times the volume for the acid is equal to the molarity times the volume for the base. And you get the exact same answer, 0.30 molar, as if you would have taken the molarity times the volume to get the number of moles, and then use the number of moles and divide it by the volume, and you get the same thing. So in other words, I'll show you how to use that shortcut here too. How many milliliters of 0.02 molar potassium hydroxide will completely neutralize 15 milliliters of 0.4 molar nitric acid. I'm going to write that equation out just so you see the plan. You have potassium hydroxide and nitric acid. They react to form water, H2O, plus some kind of base. And the base is made of the potassium and the nitrate. So it's KNO3. The potassium goes with the nitrate. The hydrogen goes with the hydroxide. Hydrogen and hydroxide together make the water. So it's a base and an acid make water and a salt. This is the base because it has hydroxide, and the hydrogen ion is the acid. ACID, there we go. So all the time, the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. We're trying to figure out how many milliliters of 0.2 molar potassium hydroxide, that's the base. So the volume of the base is equal to the molarity of the acid times the volume of the acid divided by the molarity of the base. So the molarity of the acid was 0.4 molar, and the volume of the acid was 15 milliliters, and we divide that by the molarity of the base, 0.020 molar, and it's 375 milliliters. The volumes are wildly different because the concentrations are much different. This concentration is 20 times greater than that concentration, and therefore this volume is 20 times greater than that volume. But in the end, the number of moles of potassium hydroxide, the number of moles of nitric acid are exactly the same. Now, this value here has two significant figures, and this has three significant figures. This only has one significant figure. So it turns out that this one significant figure or one significant digit in nitric acid is a pretty low precision. You don't normally have such a low precision, but because this only has one significant figure, it's actually most appropriate to make this answer only have one significant figure as well. If you happen to know this was 2 or 3 significant figures, then you could be 380 or 375, but because that only has one significant figure, 400 is best. Okay, then number 3, uh, you've got sodium hydroxide and hydrochloric acid. I wrote this reaction for you yesterday, but you've got a volume and a molarity of the base and a volume of the acid. We're trying to figure out what was the concentration of the acid. So the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. What's the concentration of the acid? That's the molarity of the acid is equal to the molarity of the base times the volume of the base divided by the volume of the acid. So you take the molarity of the base, that's 0.765 molar of the sodium hydroxide, times the volume, 86.2 milliliters, divided by the volume of the acid, 30 milliliters. So it turns out that the ratio of the volumes is the same as the inverse of the ratio of the concentrations. So 0.765 times 86.2 divided by 30, it's 2.20 molar. I think that's right. 0.765 times 86.2 divided by 30. Yeah, so it's 0.2198, but we have 3 significant figures, so 2.20 molar is the best. Okay, now, titration can work in one of 2 ways. You can either have a base that you titrate into an acid, so you could have a base with a known concentration that you're titrating into an acid, or you could also, in this problem, have an acid in the burette and you're titrating into the base. All the time, whatever's in the burette is the standard solution. It's the one that you know the concentration of, and you can measure its volume by the difference in volume of the levels in the burette. The thing that you're titrating into is the thing with unknown concentration. So in some of these problems, we were calculating the molarity of the acid. In number 2, it was the molarity, or number 2 was a volume of a base, and number 1, it was a molarity of a base. The unknown is always the thing that's down in the beaker that you're titrating into. And the burette contains the standard solution. By saying standard solution, it's the solution that you know the molarity and the volume of. Because the molarity, you make a standard solution where you know the molarity, and then you measure the volume as the difference in volume here. So this problem says you're titrating an acid into a base to determine the concentration of the base. This acid is the thing that's up in the burette, and you're titrating that, or you're letting that run into the base. And this is the unknown, because you don't know the concentration of the base. The end point of the neutralization is reached, but the stopcock sticks slightly and allows a few more drops of acid to fall in the solution. In other words, this base would have phenolphthalein in it, and it would be pink, and you're running acid into it until it becomes clear. So the 2 different ways that you can run the reaction is because phenolphthalein is in the unknown concentration, the phenolphthalein in acid begins as colorless and changes to pink as you add the base, and the end point is when it's very, very faint pink. In the case of phenolphthalein in the base, this starts out as being pink, and as you add the acid, the end point occurs whenever the solution is also like at a light pink. But if you put too much acid in, this solution will end up to go colorless, and it'll stay colorless. So the problem is, if you're trying to figure out the molarity of the base as the molarity of the acid times the volume of the acid divided by the volume of the base, if you add too much volume of the acid, So in other words, if the volume of the acid is too large, then it turns out that the molarity will be too large. If this is too large, then the molarity of the base will be too large. What I'm saying there is, if you use the correct volume of the acid, and you've reached the end point where this is a faint pink color, then the molarity of the base will be correct. The concentration of the unknown will be calculated correctly. But if you run too much acid into it, so that this value is too large, then the molarity will be also too big. And there's kind of no way to go back and fix it. You could say, well, can't we just add a little bit more base? Well, you could, except that would change the volume of the base that you used, and you'd have to consider that the volume of the solution is not only the volume of the base that you started with, but it's also including the volume of the acid that you added, plus any amount of extra base, uh, excuse me, that you put in. Sorry about that. So anyway, you'll see how this works in the lab itself in terms of adding base to acid or adding acid to base. But all the time, you want to try to end up with the solution being like that faint pink color. So let me make a note here. This acid, it starts colorless, and the base, it would start out to be pink. And in both cases, you're trying to drive it to that faint pink color, either before this changes dark pink or this changes from dark pink to colorless. And I say colorless because we don't say clear. Clear is a bad description because you can have a solution that has a color and is also transparent. So clarity refers to transparency. So you would say that water is both clear and colorless. It's clear in that it's transparent, and it's colorless in that it doesn't have a color. But if you were to take like a gallon of water and put 1 drop of blue food coloring in it, that water would still be clear. You could still see through it, but it would be blue in color. So the words clear and colorless have different meanings. It's difficult to say that something would be colorless and opaque or not clear, but the word clear doesn't mean that it lacks color. Colorless means it lacks color. Clear refers to its transparency or its clarity. So anyway, this is all recorded too, so if you need to refer back to it, you can. Hopefully those made a little bit of sense, and we'll do a whole lot more practice with titration, but we'll go over some other titration concepts tomorrow. Make sure you check in the class tomorrow so I can take attendance. And then when we come back on Thursday and Friday, we'll do a titration lab so you can, get practice with trying to reach endpoints and doing calculations with it. If you have any questions, you can put it in the chat or send me a message on Schoology or something like that. But otherwise, that's it for today, and I'll see you tomorrow. So you got a couple minutes before your second period class. See ya.